Assalamu alaikum. I'm Hamza Asad and I'm presenting our data structures and algorithms group project on behalf of my group members Faiz Hasib and Tamur Hamid. Our project topic is image compression using Huffman encoding, and since this is quite intensive topic, let's just dive right into it. So before actually diving into what is image compression and what is a Huffman code, we need to understand what are prefix codes. So in digital image and processing, you have a way to encode the data, right? Is for transfer of data or for storage, you need to maximize the efficiency of how much space it takes, basically, or how much it is required, how much space is required to transfer the data. So for that, basically, you assign symbols for each character, for example, or each color, and you basically count how many of those characters or colors there are in a particular image or a text, and then you encode that data into a prefix code, right? Now, with that prefix code, it leads to some ambiguity. Like a naive approach to a prefix code is just basically assigning bit streams. So bit streams are basically um, how data is encoded, and you need that to actually encode the data and compress the data, right? So basically, all the prefix codes are made up of binary zeros and ones. And this is what we will be looking on later on in Huffman coding and all that. So when you encode something, then it gets stored in this binary, right? And these prefix codes generally need to be unique because, for example, if I had let's look at this prefix table, for example, if I had this prefix table and I were to want to compress the sequence AAB, that would become 0 1 and then 0 1 and then 1 0. But you will notice here that there is a C and a D as well. So those ones and zeros could easily correspond to C and D if we would not know what kind of differences there are, right? So basically, Huffman codes stop this from happening, and they assign unique prefix codes to each character such that they are very easy to decode when from the table that is generated. So let's just dive into algorithms and how Huffman coding works. So when you build a Huffman tree, you're basically think of it as a binary tree, right? On the left side, there are you start with the root node. You don't start with the root node, you'll start with the leaf node, and then you build a tree based on the root node. So you have characters that occur at certain frequencies throughout a text, for example, if you're compressing a text file. Then suppose the letter A occurs 14 times or so. Then letter B occurs 20 times or so, and then letter C occurs 25 times or so. And moving on, uh, basically what it does is that it takes the least frequent characters and it encodes them. It takes the least two frequent characters and it takes them as leaf nodes, and then it sums up their frequencies together, and then it forms a new root node, and then it keeps on repeating for each node that is left until there is only one node left, and that is called the root node. So that's basically how Huffman tree is constructed. And one key point to note here is that the least frequent character is always the farthest, right? And how does this help us in generating prefix code? So basically, when you form this tree, right, you notice here that when this tree is formed, there is a certain traversal that goes on from root to the leaf nodes themselves. So you'll notice here that there are zeros and ones. These zeros and one correspond to left and right. So, and then when you traverse from the root node to the leaf nodes, uh, you keep on building these prefix code as they go. So you ensure that each prefix code is unique by this graph traversal, basically. So 0 corresponds to left and 1 corresponds to right. And suppose if you want to go to the letter B as the table forms, then you will go from the leaf node You will go 1, 0, and then 1, and that will be the format for the B letter, right? So don't stay too much into this animation because these are Russian characters, but like it's generally the same for all characters because irrespective of how text coding works, you don't need to know about that. Just know that it's sort of a general formula for generating an encoding table or a prefix code of sorts. So when we come to image compressions, the main problem that we faced when we were looking at this algorithm is that basically it was harder than text encoding because it's very hard to read pixel values from binary data. And since so many image formats exist like PNG, JPEG, and BMP, and then TIFF and .raw, .raw, I'm sure most of you have heard of these formats. So it's very hard to take the binary image data and then run traversals over them, right? You really can't. It's really complicated. So instead, we use the Python imaging library for that. It's codenamed Pillow, and that's what we use to handle all of this. So we didn't handle how we extracted the binary data from the image itself. We just ran the Huffman algorithm on it. So that's it. I'll show you the code later, but just another applications for Huffman encoding would be that they are used to encode music, images, or communication protocols. So you have like .mp3 files or .mp4 files, stuff like that. It all gets encoded with Huffman, and yeah, so a lot of like lossless compression algorithm. So lossless is when you compress something and you don't have any loss of data. That is called a lossless compression technique. And yeah, that is basically what Huffman encoding is. It allows us to save data without loss of any data, any data in the original file format. So yeah, so in a bit, let's dive into the actual algorithm. Okay, so let's dive into the algorithm for the Huffman tree. And yeah, let's start with the basic character or text encoding of particular text. So, for example, if we have characters and suppose we already have frequencies of a characters and how many times it occurs in a text, then as you can see here, we declared it. Uh, So what we have done here is that we have created these nodes. Basically, this node class stores information about nodes and its left and right subtrees, or in this case, children, right? So as you remember from when I was explaining the Huffman tree, each root node is basically the sum of its two children, one on left, one on right, and it's a summation of both of those two frequencies, and the root node is a summation of that frequency and the characters combined. So that's what we are doing here. We declare this and then we initialize an empty node, which is basically the Huffman tree here. And what we do is we declare the node class and then we run the traversals on it, right? So we're creating the Huffman tree here, right? So nodes are basically the Huffman tree. We're appending the frequency and the characters into those nodes. So basically, this would be a priority queue of sorts, nodes. And then from those nodes, we are sorting left and right, and then we are combining, we are initializing a node class, right? We are constructing a node class. We are reading the left and right symbols from that, and then we are basically popping those left and right from the queue and then appending the root node into that. And then as the cycle continues, it continues until only the root node or one node is left. And remember that each node is basically containing information about its left and right subtrees, right? So you see here left and right subtrees, we have declared it. So these still contain information about the subtrees. We still have to do traversal. But on paper, or if you look at it from the top, right, you'll only see a root node. But in those root nodes, they are like think of them as nested list, and they contain information about their subtrees as well. And then here we are basically printing the traversal, right? So we have some example that we need to know the traversal for A, B, or C, or D. Here in this particular function, I have basically printed all of the Huffman codes for every characters, which is A, B, C, D, E, F. And you'll see here, give me a second. Yeah, so from this we have generated Huffman code. So F is 0, C is 100, D is 101, A is 1100, B is 1101, and E is 111. So these basically are generated by how the graph is traversed and how they are placed on the Huffman tree, right? So that's the basic implementation of a Huffman tree for text. And when you move on to image, then image is quite more tedious, but it's kind of a similar concept. So we basically defined a pixel node class here as well. And similarly to that, we have assigned a left and right child. You'll notice here that we have here assigned a parent variable as well, because we need to know where the pixel originally came from, because we need to know where the pixel was situated on the pixel grid, right? Because images are basically composed of pixels. And then weight is basically 0 or 1 direction, like if it lies on left or right. So it's basically defining that. And then code is basically, Huffman code. So, right, this is where we start. Let's go here. And basically we're using the pillow library, or PIL, Python imaging library here. As I said in the explanation, we are using the Python image library to read the binary data and just get the raw pixel value data instead. And here we are converting this basically to grayscale, right? So interestingly enough, why we convert this to grayscale is because what we are doing here is we are mapping individual intensities of the color rather than the RGB value of a pixel itself, right? So if you recall, you'll know that in computer image processing or anything, you have like 3 basic colors, and all the other colors are composed of like the combination or the values of those 3 colors, right? And you would expect that we would do some sort of like thing with RGB, but when we converted this to grayscale, we noticed that we could easily map out the intensities and take it as in place of frequencies, right? So for text encoding, we had frequencies for each character, and for the images, we have intensities for each pixel, right? And if 2 pixels are the same, that means they will have the same intensity. So that is what we're going off on here. And this Huffman tree is built on a pixel and its corresponding intensity, right? And then we run the basic Huffman encoding function here. And this is the actual function. We're basically taking in the width and the height of the image. We are running a for loop. We are iterating over all the pixels of the image, as you see here, right? And then you'll notice here that we are calculating the pixel frequency, right? So pixel frequency, as I said, that we still need to know like how many times those pixel intensities are still occurring. So this is what this function basically does. And when we go to its implementation, hold on. Right. So pixel frequency basically runs over the list of all the pixels that we iterated from this function, right? And it basically iterates over all of them, and it returns a list of pixel frequencies where it notes pixels, each unique pixel, and it notes how many times it occurs in the image, right? And then we are constructing a node from each pixel frequency. So basically, as we said, we are assigning the pixel tree, like we are assigning the class here, pixel node, and we are basically like passing in the parameters here. As you can see, construct node is basically constructing a list of all these objects, right? And yeah, that's what it does. And then we basically run like the similar image Huffman code here. So we generate an encoding table and we save that encoding table. And that encoding table is basically unique for each unique image, right? This for loop here, we don't need to go into depth of this because this is basically the Huffman tree, right? This is basically generating the Huffman tree. So the same implementation that I explained here, where you like do summations of all the individual frequencies, this is similar to that. And then what it basically does, it calculates the each strength or intensity from the encoding table, and then it prints out the encoding table, and that encoding table can be used to decode the image back into the original format, right? So that's about it, I think. Uh, at the forward, I haven't implemented the decoding algorithm properly yet, but all of the code still works and it generates the encoding table correctly, as you can see here. Um, Give me a second. Yeah. So for this image, for example, uh, it basically encodes a 93 and a 115. So 93 would be the red color. As I said, it corresponds to the right corresponds to the furthest one. And since you can see here clearly that red is lesser than blue here, like in quantity, and 105 is assigned to blue, then it just corresponds to red and blue. It's that. And it does that for like each pixel. So for example, if I were to run it with in sec, if I were to run it with this image instead, it could also generate a tree for that. Let's just run it later. And um, yeah, so as you can see here, since this is a more complicated image, it generates like more pixel values or intensities for each color, right? So some of them are brighter, some of them are darker, and each of them have their own unique Huffman code, right? And this is basically what's called an encoding table. You store that alongside with the compressed image, and the process for generating a compressed image is actually different than the Huffman tree itself. Huffman tree is basically generating an encoding table, but the process of compressing it requires some additional steps that I have not implemented. So basically, it generates the encoding table, and that encoding table can be used to decode the original, the actual decompressed image and compress it back, revert it back to the original uncompressed image. And yeah, I think that's about it. It took a while and a lot of hard work to implement all of this. And hopefully, hoping for the best in grading. And thank you for listening, and goodbye.